what we have is presentations. My God, it is bright up here. What we have is presentations from some of the students who are supported by the foundation, and we want to get the energy back in the room. So what we're going to do is to restrict the students in the amount of time that they're allowed to talk for. So just 3 minutes. This is the time when the research leaders of the future get to tell us about what they're doing now, and there'll be a prize for the best one. But it is worth saying that the students who you're going to hear from now have already been through a selection process to get this far, so they've already proven themselves in order to get here. We have a judging panel who are scattered through the audience, and the intention was that then sort of the judging panel was going to be led by an international expert, but then time got short and they asked me to do it instead. So the first speaker is Apostolos Grammatikopoulos from the University of Southampton. He's going to talk to us on use of additive manufacturing for elastic ship models.
Good afternoon, everybody. My name is Apostolos Grammatikopoulos, and I am a second-year PhD student in the Fluid Structure Interactions group in the University of Southampton. Motivation for my research comes from accidents like this, which clearly demonstrate that our knowledge and understanding on ship structural loads in waves is still incomplete. Hydroelastic experiments have been around for decades. The current convention is to construct models in rigid segments to be joined by means of either flexible backbone or a series of flexible joints. Now, in pursuit of more detailed structural response, some researchers have produced continuous models with an accurate internal structure, the so-called elastic models. However, the increased complexity and cost associated with their production, combined with the fact that they cannot be modified after manufacturing, discourages the scientific community from using them more extensively. So the aim of this project is proof of concept of the production of elastic models using additive manufacturing. Furthermore, of the potential of the resulting model to be used to extract more information than from a segmented one. Design of an elastic model can be quite challenging, as it involves concurrent scaling of the external geometry of the ship, of its mass, and of its bending stiffness. And as may be seen here, for the model of a Lee Under-class frigate, identified an appropriate combination of material and wall thickness may not always be feasible. The model selected for the purposes of this investigation is the S175 container ship, which may be manufactured using a cellular cross-section, much resembling a full-scale container ship. Additive manufacturing, and in this case 3D printing, may greatly facilitate this process. However, it involves some challenges which still need to be considered, such as the maximum build volume. More importantly, the way the mechanical properties are derived by the material manufacturers result in little information relevant to this project being available. As a result, an ongoing material testing investigation is going to provide us with the necessary data to finalize vessel design. The model is to be constructed in a series of sections to be joined by either welding or adhesives. The continuous structure will then be subjected to a series of dry and wet tests. And the results will be used to validate the concept and also to assess possible advantages compared to segmented model testing. Production of entire ship models with a fully integrated system of 3D printed sensors is expected to become available in the near future. Thank you.
Will you be able to do vertical bending and torsion at the same time, or would that be overdoing a bit?
So that's a tricky question, actually. You got the point. So the plan is, as you probably already know, modeling the appropriate torsion characteristics. It's much more complicated because we need to have to be very precise about the distribution of torsional stiffness and also about the location of the shear center of the cross-section. Given that there are already several challenges within this project, we decided to start with vertical bending. If that works, we could proceed to try and model the torsional characteristics as well, but it's not in our primary objectives.
First things first. Actually, we just wanted to ask about the 3D printed sensor technology. How advanced is that at the moment? Have you trialed it already?
So we haven't tried it ourselves. There are currently there's currently a series of publications by people who have actually used 3D printing in order to produce strain gauges. And it's been quite successful so far. They've used it among others. This one is from application on elastomers. It's been quite successful so far, and so we are positive that it's going to become part of this project eventually. I don't know how soon. It depends on the equipment capabilities as well.
Great. In the interest of timing, I'm going to move us on. Thank you very much indeed.
Thank you.
Yep. Yes. And so the second talk is by Hodja Muhammadi from UCL, who's going to talk about improving air quality by traffic management and control.
Believe me that I didn't want to start my presentation with the news about the dead, but there's a painful truth that nearly 9,500 people die early in London because of the long-term exposure to air pollution. Not only London, but almost every major cities in the world face seriously to the air pollution problems. But why we have air pollution? Different sources are accounted for the air pollution, such as industry, agriculture, and transport. Road transport is an important source, and it plays a much greater role because it's concentrated on the road networks in the cities and towns where there are usually high densities of living areas. And what we know about the road transport emission is that it can be changed by various items from fuel type to ambient temperature. But in the field of transportation engineering, the most effective way to control and reduce emission is traffic management and control, which is exactly the topic of my PhD project. And how we want to do this? Imagine the situation that you are driving in the road and you are facing a red signal light. You have to stop until the green light, and then move again. This simple process contains 4 phases: cruising, braking, idling, and accelerating to move. The point is, changing the duration of each phases or the intensity of braking or accelerating can change the vehicle emission. And I'm looking to model this relationship in my PhD. Actually, this project has 2 main parts. The first part is to find the relationship between vehicle movement variable, something such as speed, acceleration, and power, and its emission. It was done by a statistical analysis and modeling. Then this model is connected to the second part, traffic flow model, which can estimate accurately the effects of different traffic policies on air pollution. As a result, we have traffic policies that can change and reduce air pollution, and they can be applied in our roads all over the world, so we can live in a better and cleaner world. Thanks for your attention.
Thank you. I thought that was really interesting. How would you describe what you do to your parents?
Maybe I'm talking to my father and said that when you're driving in a street, your vehicle emission depends on the way of your driving. The harsh acceleration, harsh braking, and the maybe highest speeds can increase your vehicle emission. And based on my model, if you drive and obey the traffic policies that I organize in the city, you can decrease the emission from your vehicle.
Well, I've got one, which is, if you look at the data that you're going to be getting out of vehicles, will you be able to put into the model driver behavior as well? So what the driver does influences what the engine does, which then influences what the emissions do.
Yes, actually the input of the model would be the vehicle movements, speed and acceleration. I don't want to specialize my model into the one driving way. I want a model that is general and can capture all the driving cycles and driving ways. So the inputs would be only a speed and acceleration of the vehicles that can be obtained by the various items in the city.
Okay, thanks. Thank you very much. Next up, we have Gabriel Levada from Nottingham, who's based at the National Structure Integrity Research Centre, whose title is How Electricity Can Help Generate More Efficient Electricity.
Cake. Who doesn't like a good cake? But what makes a really great cake? Good ingredients, of course, but the baking process is crucial. And how do you know if your cake is baked or not? Well, you take it out of the oven, you stick a toothpick or a knife in it, and if the knife comes back clear, then it's done and you can serve it. But let's move a bit away from cake for the moment, and let's have a look at the wind turbines industry. Today, the UK is the world leader in terms of offshore wind turbines, and it's aiming at generating enough energy by 2020 to roast about 13 million Sunday roast. However, wind turbines do fail, and especially the blades failed. So, these failures are due to defects inside of the blades. Knowing that those defects are happening during the manufacture process of the blades, therefore, we need to monitor that manufacturing process. And it's not that different to make a blade and from making a cake. You mix your ingredients, you pour them into a mold, they are kind of liquidy, you bake it, you heat it, and then you take them out of the mold. Magic. Well, not really, science. But the idea is that during that process, the conductivity of the material of the blade is changing. So what about monitoring those variations to know when your blade is fully baked? Well, that's the subject of my PhD. And how am I supposed to do that? Well, you've got here the mold. On top of it, you've got the blade. And in between, you've got the sensor, which is, well, basically wires. On those wires, you apply a difference of potential. This difference of potential creates an electric field. And by monitoring the variation of this electric field, you've got a signature of the blade baking process, which you can compare, therefore, to a perfect blade signature, and then tell, well, your blade is fully baked, or you need to pay a bit more attention and maybe do a little tweak to your recipe. Thank you very much.
Thank you. And questions, please.
Thank you very much for that. Very interesting. I liked your cake analogy. And Louise Sanger, Lloyd's Register Foundation. Presumably, your sensor then is baked inside the blade? And
actually, no. I'm looking to develop a sensor that would be completely included in the mold. Therefore, you don't have to worry about any kind of differences in your blade strength, and you don't also have to worry about the reproducibility of a sensor each and every time. So your sensor will be embedded in the mold, so you can rely on that sensor. If you've got the baseline of that sensor, you've got the same signature for that sensor for every blade you will produce afterwards.
Hi, Galata, it's Rebecca. I was wondering whether you can talk about the avoidance of wastage through poorly manufactured blades versus this point about them failing in service. Will the method actually also help reduce that wastage when it's difficult to recycle composites?
That's also a very good point, because the aim of that PhD is to be able also to say, in the middle of the process, you've got a really big problem here. Maybe stop completely the making process of the blade, even when it's not fully baked or cured, as we say, and therefore prevent the industry from making the blades entirely and then doing some non-destructive testing afterwards and discovering that the blade is not fit for purpose. So you can stop the production of the blade at a very early stage, so prevent from a big loss in material, energy, and money. The other the other application of that kind of monitoring would be also to be able to say, okay, you've got a defect in your blade. It may be in your acceptable range of defects, but you may want to monitor that blade with either embedded sensors, or you may want to monitor that blade and check that blade on site instead of once every 6 months, once every month, and at that particular place, because if the blade is likely to crack at one point, it will be there.
Thank you very much. Okay, so next we have Alexandra Morato-Kazadamant from Aberdeen, who is going to talk about reliability analysis of offshore wind turbine support structures.
Hello, everybody. My name is Alex Morato. I'm now in the last stage of my PhD, which I'm doing in Aberdeen, within the framework provided by Lloyd Register Group and Lloyd Register Foundation, and also with the help of my 2 supervisors. And today I'm going to give you a brief explanation of the computational framework that we developed to analyze the reliability of offshore wind turbine support structures. Basically, offshore wind industry is rapidly developing, but relatively immature. An example of that are the codes and standards, which propose a series of design load cases which imply thousands of simulations. If we add to that all the uncertainties present in these systems, we come to questions such these ones. So is the industry delivering the optimum structure? What are the actual safety levels achieved by following these standards? And that's, these questions are the ones that the PhD tries to or wants to answer. So the first essential step is to analyze, to understand these design load cases proposed by the standards. So we picked a set of candidates to be the most harmful design load cases for the structure and substructure, and we analyzed them thoroughly to understand and to study the effect of the wind and waves, as well as the influence of the controllers. So we came up with a ranking of the most severest design load cases, so we could focus our priority. Then we had, as there is no an integrated software capable of capturing the offshore loading and performing at the same time comprehensive structural analysis, we had to develop one. So we created a framework, a computational framework based in an interface between FAST and a finite element analysis software, Abacus, so we could perform stochastic time domain simulations. So we got the loading, we got the tool. So we got a problem as well, because each simulation took so much time to run, so traditional reliability methods became unfeasible. So we proposed a new approach to analyze the reliability of such structures based on a surrogate model named kriging. Basically what it does is it substitutes all this computational framework with a transfer function. So with this transfer function, we then can apply typical reliability methods like Monte Carlo simulations or first or second order reliability methods. And the ultimate goal is to recalibrate these safety factors using all this framework. Thank you very much.
And questions, please. Okay. So how do you take the sort of the data of the load cases, yeah, and get that into the model? I mean, how is that done through the model boundary conditions?
So, well, basically the load cases give you like the loading, the wind loading, the model that you use, how many years return period are you going to take into account, and the same for the waves. So you put all these inputs in FAST, which transform this data into forces. And then you can run the simulations. And was that your question? So how we get these points? Yeah. So basically, using this framework, we can get the sample points. And with a limited number of sample points, we can find this transfer function, which allows us to substitute the whole computational framework.
Okay, thanks.
I'm just having a query here about the kriging method. The points they used to develop the kriging method, do they primarily fall into the the failure domain, or are they just generic? And how do you validate that part, which I guess you're most interested in, will be sufficiently accurate?
Yeah,
Thank
that's
you.
a good question. Actually, we found sample points using a typical random sampling technique, so it's not around the failure region, so it's just around all the range of the variables. We validated the accuracy of the method, but we did it in a number of ways. So actually, if one wants to take this method further, the next step would be to, or even add a second step on the framework, so we can see where is the region, like the failure region, and perform the same thing again, the same method. Or there are now different. I was in a conference in Glasgow 2 weeks ago, and there was a guy also trying to develop a method for that, which was based with a subset sampling simulations using subset Monte Carlo simulations, which tried actually that, so to focus on the failure region. If we had more time with that, it's very interesting, so we would spend more time on that, but we had to carry on as well in the research.
And next we have Susanna Nabor from the University of Nottingham. Her talk is on modelling risk on an ageing underground railway with a Petri net-based approach.
So it's a little bit technical, so I'm going to try and whiz through. So modelling risk on an ageing underground railway with a Petri net-based approach. So obviously as your system ages, your components get older, they're more likely to fail. You need to make sure you've got a really good maintenance strategy in place to ensure that these failures don't occur, especially on safety critical systems such as an underground railway, where these failures can have catastrophic consequences for your passengers. So a Petri net-based approach is very applicable because it can handle dependencies between these different components in your system. It also can incorporate complex maintenance strategies and also any failure or repair times. Okay, so there's two types of nodes in your Petri net. You've got your places and your transitions. Your places are marked by tokens, and these can represent states of the system or any sort of activity like maintenance or inspection, and they can also be used to count time or the sort of activities that have taken place. Transitions allow changes to take place within your system, and they can allow your system to progress as time goes on. So the PetriNet model can be built to represent plenty of systems, including those in an underground railway, and it's also possible to simulate it quantitatively. So a little bit about this. You can use Monte Carlo simulation to simulate this model. You need to assign probability distributions to your transitions, and then for each run of the simulation, you step your tokens through your net, and this represents the changes that take place through your system over time. You then take your model outputs out of the net. These could be how long the tokens spend in each place or the amount of time it takes to reach a certain place. And these outputs you take as your output of the model, and then with each run with your Monte Carlo simulation, you get a convergent average. As you can see here on the right, for a very simple PetriNet model with two distributions assigned, you can see how this convergence happens over time. So here you can see a slightly more complicated version that can be used to represent the different degradation pathways in rails. All these different places can represent the different sort of states that the rail can be in. Below you can see inspection strategies, and on top of this you can add a maintenance layer. This maintenance layer can include opportunistic maintenance and emergency maintenance, and you can then use this to optimize your maintenance and inspection strategies so that you can reduce your risk the best you can for the resources you have available. Thank you very much for listening. Does anyone have any questions?
Hi, I'm Aditya. I'm coming from Catapult and Imperial College. I would like to know whether you could predict traffic signal failures with this.
Traffic was that?
I mean, signal failures for
Oh, yeah,
trains.
it has been done for signal failures. There's someone doing it in my group. So you can basically take any system and you just need to look at the dependencies and the different, you could have dependencies between component failures or between maintenance. So you repair one signal, what happens to the next signal? And you can kind of tie in any links between real-world systems into a model like this and then use it for this sort of simulation optimization.
Is there an accuracy rate, whether you're able to, did you validate it with the real-life situations and see whether your models did predict accurately?
So at the moment, I'm looking at a bit of work on switches and crossings. So I've pretty much built the model and I'm incorporating the maintenance, and then I'm looking to get some data in, and then I'll match up the two and see. So hopefully, yes.
Cool, hi there. Doug Owen from the Shoemaker Institute. Really interesting bit of work. I just wonder if you can say something about the assumptions that you made about the effectiveness of maintenance and inspection strategies built into the model. Did you assume that they were always 100% effective and restorative, or something different?
No, so you can assume a really good example is if you consider tamping of tracks. So obviously every time you tamp a track, the condition can get worse because you break up the ballast. So it's possible in transitions like this to add in conditional transitions based on the number of maintenance activities that you have completed or the type of maintenance activity. So you can incorporate maybe several different types of maintenance into these transitions and split them into different distributions depending on that. So you will have to make some assumptions because it is kind of not a completely continuous model, but you can add more continuity into it.
Thank you very much. Great.